The rules for sketching graphs. You see, I mean, it doesn't matter whether it's maths, whether it's science, social science, whatever. If you're collecting data, we like to represent it somehow, and we usually represent it with a graph. It's a very common way of representing data. So you collect your data, you put it on a graph, and hopefully you see some pattern emerging. Right? So the pattern determined by the shape. You may have heard the term line of best fit. Heard that expression? So you plot your data. It might not lie exactly in a line, but that's because of experimental errors and things like that. But you draw a line of best fit, and once you get a straight line, you know that there's a direct relationship between the data. As one increases, the other increases, and so on. Or you might plot the data and get something that looks like a hyperbola. In that case, you know it's inversely proportional. As one increases, the other decreases, and so on. And other common ones, you get log curves and things like that. Okay. So once you can approximate your data with a known function, then you can analyse that data a lot easier and make predictions. If you can come up with an equation for the curve, you can predict what's going to happen in the future by just plugging into the function. Scale. So when you're plotting your data, it is important to have a consistent scale, because if you don't, then the shape that you're looking at might be distorted. If you don't have an even scale, imagine if, I don't know what sort of experiment you would have where the data would end up being in a circle, but just imagine it did, and you didn't have a consistent scale, you'd look at it and think it was an ellipse rather than a circle or something like that. Known functions, easily sketched from key pieces of data. The intercepts, of course, are the obvious ones. Y-intercept, sub in x equals 0. X-intercept, sub in y equals 0. You can find where it cuts the axes. Now, once you've got those sort of information, if you know the basic shape, you can get a rough sketch. Okay. There are specific features that certain functions have. So there are things to look out for when you see the equation. And if you're ever in doubt, don't ever forget the most basic idea that you would have looked at probably in year 7 or even earlier, and you probably do it in science all the time. Draw a table of values and just plot the points, and then you might be able to see the pattern. Okay, the first function we always look at is that linear function, because data often is directly proportional. Very important function that we have. And I guess the most basic of them all would just be y equals x. There it is there. So any data, as I said before, if it demonstrates direct variation, then it will end up being a straight line on the graph. Okay, so this is called the linear function. Okay, I talked about best fit before. So yeah, so if you do your line of best fit, you can then approximate with that linear function. Y equals x is the most basic of them, but every straight line can be transformed via translations, rotations, reflections, or a combination of those. You might, again, going back to year 7, you might remember you might have spent some time talking about rotation, reflection, and think, what on earth are we talking about this sort of stuff for? What use is it? Well, here's one of the main uses for it. So how do we recognise it? If for some insane reason we go, what is this function? We don't recognise the straight line. You may recognise this form, y equals mx plus b. Okay? And okay, even then, what are we looking for? Look, y is to the power of 1 and x is to the power of 1 as well. That must be a straight line. So, terms that contain at most one variable, and all the variables are to the power of 1. When expressed with the dependent variable as the subject. So when we have got it as y equals mx plus b, we've made y the subject, then we know that the slope of the graph will be the coefficient of x, and we know the y-intercept would be the b. So that's our linear function. Then there's some special straight lines which only have one variable. So parallel to the x-axis, we end up with y is equal to some constant value. So that one would be y equals 2. And parallel to the y-axis, x equals some constant value. And so that's x equals 3. Show that we often get questions in maths which simply say, show that. So all you really have to do is show that it works, that this is indeed true. So the best way of showing that is just to substitute straight in. We just have to show that x plus y is equal to 6. So, x plus y, well, hang on, that's 2 plus 4. Oh, what do you know, that equals 6. So yes, it is true, it does work, therefore 2, 4 lies on the line. So I don't know how you're used to setting this sort of question out, but you've got to imagine someone is going to be reading your solution, you're explaining to them what's happening here. So you don't just go, oh yeah, this is equal 6, thank you, I've finished. Come up with a conclusion, I guess much like an experiment really. Okay, what can we conclude from this work that we've been doing? Well, 2, 4 does lie on that line. X plus y is equal to 6. That's a quick one.